Here we are using an electric beam engine model to demonstrate the Gantner test equipment and some of its capabilities. This is an old model company beam engine, and it operates with two banks of coils and an armature, and these switch on alternatively with the two contactors from this cam drive shaft here. If I wind it round a bit, you'll see the contactors turning on and off each coil. So this contactor is connected to these two coils, and this contactor is connected to these two. We've got an on-off switch, and we have a flywheel which keeps the momentum. So as the cam goes to the top, the momentum of the flywheel keeps it on turning until the magnets turn on and pull it down. So we have connected to it a Gantner Q.Station 101 and some I/O modules. We've got an A101, we have an A107, an A102 and a D101. The main screen is shown on the HMI, and this contains all the information about the I/O modules. You can see all the process variables here, and we've made a custom screen which has all the variables that we are interested in for this demonstration. We've got a start-stop button to start the engine, and we've got a speed control to control the speed of the engine, and we also have the coil temperatures, current, strain, spine and the vibration, and we've got a graph trend plotter showing the speed variation over time. If we see the connection to the I/O modules, we've got in the A101 pins 7 and 8, we have a Ditran accelerometer which is positioned just here, and that's picking up vibrations. We've also got a in the second connector, pins 2 and 3, we have a strain gauge. So it's a quarter bridge strain gauge that is attached with super glue to the spine here. And in the A107 module, in pins on the first connector 2 and 5, we have the connection to the drive circuit, and the drive circuit has a shunt resistor, and this is monitoring the voltage across the shunt resistor to give us our current load from the motor. In the bottom of this connector, in pins 7 and 10, we are connected to a magnetic pickup. So this magnetic pickup is very close to the drive shaft, and as it rotates it will give us a reading, and this has been used with some Gantner signal processing to give us our speed. So the faster it goes, the more revs per minute we have. Then on this terminal block, which is a special terminal block for cold temperature compensation, we have a thermocouple in the first two connections. This is positioned just behind the coils, so we're monitoring the coil temperature. And then finally in the A102 we have an output, and this is the voltage output, which goes to the speed control of the motor. So in theory, the more voltage you have, the faster the motor should spin. So the switch is being turned on, and we can turn on the screen, press the start button, and then if we give it a flick, it should kick into action. And we can see if we were to reduce the speed down to 6 volts, for example, you can see the speed of the motor has decreased. And we can also verify that with the speed RPM here, come down to about 200 RPM. Also on the trend here, you can see the speed reduced over time. If we gradually increase the speed, 8 volts, see the speed is increasing. Increase it further, 10 volts. And the speed we're monitoring gets up to about 600 or 700 RPM on here, and that's the maximum that this circuit can handle. At the maximum we're getting a coil current, bear in mind it's alternating, at around an amp. Our coil temperature is rising. You see there, temperature's rising 30 degrees. It's about 25 degrees ambient in this room. Spine is rocking all over the place, so we're getting the spine continuously changing the strain, and the vibration also is continuously changing. There you have it, the old model company electric beam engine, and we're using it to demonstrate the capabilities of the Gantner Instruments smart controllers and I/O cards.